Yeah, Andreas, thank you so much for providing us with these, I would say, great examples. Um, the I think the thing that we learned somewhat, but when looking at those examples, is first of all that the approach that we discuss and that we provide, or the solution approach that we provide, is in general very flexible. So there are lots of problems that you might want to solve with those. Um, but obviously, as Andreas already explained, the approach that we are looking at at the moment. So the first um, the first attack, so to say, um, is not very helpful in most of the cases when we really want to find a solution. Okay, the reason why we are discussing this is that you basically see where the general idea how to think about solving those problems comes from, starting from scratch, from a situation or from a method, from a methodology that you already know. So I'm not saying that the Lagrange approach that we're discussing here, that I will present today, is the most clever one to use when solving those problems, for a number of reasons. One of the reasons is, as Anna has already said, that the number of equations, so the system of equations that you want to solve, so the roots that you have to find, tends to be very complex. This is one thing. The other thing is that that many of the problems that were just talked about a minute ago are, for example, characterized by I don't know, by inequality constraints, by non-negativity constraints, and obviously you can use those, or you can integrate those constraints also into a Lagrange approach. Um, but everybody of you who tried, even in a static setting, to integrate inequality constraints knows that this tends to be a big pain. So usually you wouldn't choose this way. You wouldn't choose this method to move on. But again, this is just to motivate the general solution idea, and to motivate why other solution ideas exist. Okay, and sometimes in many economic applications, for example, if you look into growth theory or in some parts of growth theory, a variety of this Lagrange approach is relatively common. So I think it's a good idea to walk you through this. Um, do you can you see the slides, and can you hear me good? Is the perception okay?
Yes, everything is all right.
Okay, awesome. Thank you. So um, we stopped, I think, last time somewhat, I think, here or here. So again, what the Lagrange approach does is, as always, we look at the objective function, which is just the sum of all the contemporaneous utilities, all the contemporaneous gains that you would receive, and we want to maximize this objective function by choosing not only one variable or two variables, but by choosing a path of all controls over the planning horizon, which runs here from t0, from today, up to capital T. That could be obviously 2 periods of time, 3, or whatever number of periods of time that you would like to have. And we do not only think about choosing the controls, but implicitly, in a sense, we also choose the number of the sequence of states, because as you might remember, the state also potentially enters, the utility function. Okay, so if we were looking at this objective function, then we would like to pick a path for the esse, and the path for the C's. Okay. The problem, however, is that we are not free in choosing the states, right? Because I can, in a sense, choose future states, but only in a specific way. So in every period of time, I, as a decision maker, has to obey to this transition equation that tells me, starting from a state that I'm in today, what will be the next period state if I choose some control, right? So this is why you have to consider this restriction, this equality restriction, for every period of time. Okay, but in a sense, this is nothing. This is nothing far from the standard Lagrange problem that you know from I don't know, consumer theory. Okay, where you said what is my goal? Well, I want to maximize my utility by choosing, I don't know, 2 consumption variables, and I have to take into account that that the consumption variables that I could choose are somewhat related via the income constraint. Okay, and the same idea here is true as well, right? We are choosing the control path and the path of the states, taking into account that the states and the controls are somewhat related with each other. And what we assume here is that, first of all, this relation is deterministic, since we're talking about deterministic model. So we know for sure what the state will be in next period. And we assume that this relation, so this transition relation, is exogenously given for us. So the planner is not capable of changing this functional form. Okay, so what we then have is we have a fairly standard maximization problem, which is just basically blown up due to the time dimension. Okay, since we consider not only one point in time, we have to consider this restriction or this idea at every point in time. So what we are then at the end of the day have is we would have 2 times capital T plus 2 endogenous variables and capital T plus 1 restrictions. And note that this only holds, and this is again just for simplification, right? For a situation where we have just one control and just one state. But obviously, you could have as many states as you wish, and you could also have as many controls as you wish. Okay, but then you would see that the number, that the size of this maximization problem blows up, right? Which tends to be a problem in many applications, and which tends to be a problem also later on. Okay, now what is the general idea if you have a maximization or an optimization problem with a restriction? Well, you set up the Lagrange function that directly takes this restriction into account. And since we know that we have here an equality restriction, so the decision maker has to obey to this transition equation. This is very, very easily done. So we do not have to really take any, I don't know, a complementary slackness into account, but we know that this will hold true, such that we also know, if we write down the Lagrange function, that this is 0 as well, so that we know that the shadow value is always a positive number. Okay, and the shadow value reflects, basically, we see that in a minute, reflects the constraint, or the value of the constraint that I have to take into account. Okay, so this is just the utility function, and these are all the constraints that you have to take into account. Okay, and the reason here is that you have I mean, in your standard Lagrange equation, you would have here just one restriction, one shadow value. Sometimes this is also labeled as a lambda. We've chosen the mu for whatever reason, and what we have here is we have just this t+1 different restrictions that I have to take into account. Okay, so this is the objective, and these are all the restrictions. And you could also add additional restrictions. Okay, you could, for example, add that I don't know, the state is not allowed to be negative in addition to this equation, or you could assume that the control has to stay in a different region, or that the state has to stay in a different region, and then you would add, as you would do in a standard Lagrange problem, you would add all the constraints that you have to obey, either in every period or in all period or in some periods. You would just add here all the additional constraints. From a conceptual point of view, conceptual meaning just I'm writing down the problem without having to, you know, put my head on the block to really find the solution. This is very trivial, okay? But really doing that, so really incorporating that and finding the solution, and this is what we are basically after at the end of the course. Remember, the take-home knowledge of this course should be that you know how to set that up, but also to really solve this problem. So solving this problem would become very difficult, right? So this is just a just be aware of those problems that might occur. Okay, when we have this Lagrange function, and we know what to choose, right? We want to maximize. We want to pick every control and every state that maximizes this utility function. So we want to pick every state and every control that maximizes this Lagrange function, where we can then just very easily write down first order conditions for the optimal controls, right? So what we do is to get to know how the optimal control at some point in time t would look like. We have just to maximize, to take the first derivative of the Lagrange function with respect to ct, right? And then set this to 0. Okay, which is very easy. The ct turns up here. Okay, and remember, this is one specific ct. So we have the sum of all the different ct's, and we just wanna choose and wanna change one of those ct's. So one part of this sum, one part of the derivative of this sum should be equal to the derivative of this part of this sum. So we do not have to worry about the summation signs, because there's just one control that we pick. So it's the question is not what would be the change in the path, but what would be the change in just one control. Okay, so there's just one part of the sum that reflects that. Hence, we can just write a first order condition very, very easily down. And this is true, this holds true for all the different controls that I pick. So the control at time 0, 1, 2, 3, 4, and so on until capital T. So we have a system of optimal controls of capital T plus 1 equations, right? And how to interpret this equation? This is also relatively straightforward, and is very, very, very close to the standard interpretation of any first order condition in your Lagrange history, so to say. So what do we have? Okay, the decision maker thinks, well, changing the control at some specific point in time generates a contemporaneous effect on the gain. Think of the U as being utility, and think of think of the C, sorry, as being consumption, okay, then this would just be the marginal utility of consumption that you have today. Okay, so this tells you if you consume a little bit more, well then you have more, then you feel better, right? So this is the marginal effect, how you feel better. Okay, but this comes at a cost, right? Potentially comes at a cost, and the cost of the change in the control today is a little bit complex, because it doesn't pop up right away, right? So how does the control, the change in the control today, say the consumption, affects you? Well, it affects you in the future, right? Because the change in the control today changes the situation that you are in tomorrow in a specific way. This is reflected by this del M del CT. So this is the change of the situation, of the state that you are in tomorrow. Okay, and then you have to value this change. So this tells you the decision maker wants the control at every point in time be such that the marginal contemporaneous effect is equal to its change on tomorrow's state, which is then appropriately valued. And this appropriate value is reflected in the mu t plus 1. We will see later on a more straightforward interpretation of this shadow value. Okay, but what the take home message of this first order condition basically is that the agent tries to trade off the direct effect that my control has against the intertemporal effect that my control has. And the clever thing is that you basically only have to consider the effect of your control on tomorrow's state, because everything what happens from there on is somewhat condensed in this shadow value. We do not have to worry about that. And this obviously makes thinking about the optimal choice obviously much more easy, right? Because although I know that everything I do today will affect my future and every point in time of my future, right? I will be on a new track, on a new trajectory. But that doesn't really matter when thinking about the first order condition. The only thing that matters is that I have to think, okay, how would my situation tomorrow change, and how would I want to value this new situation or this change in the situation? Okay, and everything from there on, every effects that arise from there on are somewhat condensed in this shadow value. Okay, this will be an important insight later on, and this will be of great help when we discuss an alternative methodology, and which makes also the intuition behind the optimal choices very straightforward. I think. Okay, so this is the first order condition for the optimal controls. Okay, do you have questions so far?
What I find a bit difficult to understand here is that I think in many decision problems you have discrete actions that you're using, and so I'm not sure how general this solution is actually. For example, if I need to I'm working on credit decisions in credit processes, and when I need to, for example, decide between foreclosure, doing nothing, or something else, then this is not really differentiable. So
yeah, that's true. Yeah, that's true. We'll come later on into to situations where you could consider this in a way. And I think this is primarily a numerical issue. I would say, at least in my ignorant perception, because what we assume here is the most straightforward of all problems, where everything is differentiable, everything is continuous, well, except time, obviously, and you have you can have this marginal decision, right? But I mean, the general notion wouldn't really change, because in your situation you would have then, I mean, you do not have a marginal effect, right? But you could, if you have three different controls that you could pick, or two, or whatever many you would like to see, well, then you could write also down a say a discrete or an inframarginal optimal choice, right? Which doesn't really differ that much, because the general idea is, again, that you have to think about, okay, if I pick A instead of B, well, then this changes somehow the state that I'm in from tomorrow, and I have to value this in some way, right? So this wouldn't really, I mean, you couldn't calculate it in as nicely as shown here. But the general idea, I think is valid still, no? But I mean, what we assume here, I mean, this is that everything is nicely behaved.
Yeah, I think that's actually a restriction here, which we are going to relax later on. The other restriction that's really severe at the moment is that we rule out any kind of randomness. So both restrictions I think are quite relevant, but we just start with the simplest case, and then we relax the assumptions step by step.
Yeah.
But of course, it's a very valid point.
Sure. Any further questions?
Maybe not a question, but a remark. It
Sure.
just popped up to me that, well, it reminds me of an interview with a world-class chess player who had been asked, how many moves in advance do you think, or do you plan? And he answered, well, just one move, because I always have to trade off the current effect of my move, and then I just value the next situation on the board, and that's enough. So if you have a good valuation mechanism for the situation at hand, say the situation on the chessboard, then you needn't really think in advance more than one move. And that's exactly what's going on here. Yeah.
But for that, obviously, you need to know this value effect, because everything else is relatively easy to find, right? So the effect of what you do on your contemporaneous utility is easy. So it's clear. This is in this chess player thing. It's the effect that you have right now, and it's also very straightforward what happens in the next situation. So the difficult thing is how to value that, or how to evaluate that, right? Okay, so the same will be true when you pick the optimal state. Okay, when you look at what will happen to the situation that you are in the next period. So again, you trade off things. So you have a direct effect of the change in the state. You could have a direct effect on the change of the state and contemporaneous effect. But in general, changes in the state are more difficult to take, a little bit more difficult to take into account, because if you look at the at all the restrictions, then you might see, okay, if I change the state, right, then I have an effect here. So if I change the state today, then well, it has an effect on the state tomorrow, given the control. This is one effect. But you also have a directly other effect that tells you basically that if you could change the ST, and remember that contemporaneously, if you are in T, you cannot do that, so that would be a windfall gain. How would you value that? So the change in the state basically pops up in two parts of the restriction, namely in the restriction where your system, where your situation is moving, okay, on the one hand, and on the other hand, it would tell you something if that would happen. What is the effect directly on the restriction that you face? Okay, so basically, with a change in the state, if you could change the state today, then two effects pop up that you have to take into account, right? And this is the reason why here you have different effects. Okay, so you have here a gain basically of having a different state, and here the effect of how the state changes the next period state and how you would value this new situation. Okay, so the thing is, this is like when thinking about the self-driving car. Okay, the control is relatively easy. This is, for example, change in speed, or change in where to put the steering wheel. But changing the state is like picking up the car, put it somewhere else, and this picking up the car, putting it somewhere else has obviously two effects, right? You pick it up and put it somewhere else, so it changes its state. This is reflected in this mu t, the value. This is how you value the new situation that you are in. Plus, given the control, it also changes the path that you are moving from there on, and this is reflected in this part of the equation, which affects the path that you follow, which you then again value in a specific way. Okay, so the S0 is exogenously given, so you cannot pick all the states. So you cannot pick the state at point in time 0, 1, 2, 3, and so on, but you can only pick the state from 1 to capital T. So there are capital T constraints. Okay. The last thing that we have to think about is what happens what happens with the state that is basically outside of the planning horizon. So what is the state in T+1? Okay, so this is basically the idea when you are a decision maker and you think, okay, what do I want to leave at the end of the planning period, or how do I value the situation that I'm in after the planning period? When there's no restriction on this, so there's no restriction on the state that the system is in after the planning horizon, well, then the first order condition for this is just that the mu T+1 should be 0. Okay, so the value that is left at the end of the planning horizon must be 0. Okay, so this value you do not want to leave your planning horizon with anything left. Suppose this is a capital stock that you optimally choose. Then at the end of your planning horizon, you do not want to leave any capital to your I don't know, to your kids. Okay. Because in this world there's an end, and the end is the end. Okay, and this situation is called the transversality condition. Okay, and with the help of the transversality condition on the one hand, and all the restrictions that we have on the other hand, we are basically able to, or we were able to solve the system for equations in in the unknowns. So we have t+1 controls, we have t states, and we have t+1 shadow values, and we have the same number of equations that solves in those unknowns. Okay, and having a solution to this would then constitute the optimal path of the control on the one hand, and the optimal path of the control implies an optimal path for the state. Okay, so what we have is basically a large system of many first order conditions. Okay, and of many the equation of motions, and we could just solve that by pen and paper. And obviously, we do not have, literally speaking, all those many equations, but all those many equations are basically represented by the difference equations that I've shown to you, right? So this is a difference equation in the shadow value. We have a difference equation, or we have an equation in the I think this is not literally speaking a difference equation. We have an equation in the optimal control, and we have the difference equation in the state, and we could basically solve that. Okay, this is doable, obviously. I mean, this is just, you know, solving three the difference equations, or solving the large set of regular first order conditions. But the problem is obviously that general problems are relatively complicated to being solved, and it's also very tedious to do so. Usually, you would assume some simplifications to get a handle on finding a solution. Usually, you assume that the law of motion is linear, and you assume that the contemporaneous state has no effect on contemporaneous utility. This is very, very simple. So with these simplifications, these are the simplifications that you usually assume. And then you have a very simple system of first order conditions, which then give you basically the path of the valuation that you would attach to any state that you are in. Okay, and you would have a difference equation that tells you how the control evolves, and usually this evolution of the control is called the Euler equation. Okay, if you're familiar with optimal consumption planning, then this would be you would also call this a Keynes-Ramsey rule. Okay, that tells you what is the consumption, what is the optimal consumption path over time. Okay, so there are a lot of situations, as long as you are willing to make a lot of simplifications, which many theorists are usually willing to take. You would arrive at a comparably simple equation that tells you how the optimal plan, so the optimal things that you're going to do, evolves. Okay, and this is the Euler equation. In general, this is not so easy. So in general, if you want to find general solutions for general problems with a lot of states, with a lot of controls, with as we talked about, discrete choices, then things tend to get out of hands. Okay, just for you to get a better understanding of how that would work, we have just a very simple exercise about this Lagrangian approach. We have here not we've not chosen the route to assume that the state does not affect the contemporaneous gain. This is what we assumed here. because this problem that we consider here is just simple enough to show this by pen and paper. About the solution strategy and how the general idea is, and that I think most instructive in a sense, at least from my point of view, of this method, is that although the problem at first glance seemed to be relatively complex, choosing an optimal path, taking all the changes of the system into account, is, although again seemingly complicated, could be solved at least in principle by a relatively simple technique, right? By just using a Lagrange optimization technique. So if you, for example, wanted to write down an algorithm for a self-driving car, you maybe would nothing really need more than knowing how the Lagrange concept works. Obviously, this is not really true, because we haven't considered stochastics yet. But in general, this is a relatively straightforward approach how to solve those problems. But the problem is, although it's relatively straightforward, it is at some situations, or in some senses, not the best way to think about the problem, because we are totally not taking an important characteristic of those problems into account. And this is what we will see that in a second. And this is the recursive nature of the problem. Okay, so this direct Lagrange approach yields you with, or puts you at least in principle in the position to solve this thing, but with a lot of labor. Okay, it is very tedious with those large first order conditions. With this very simple problem that we've shown, it's fairly easy, but things tend to become complex so very fast. So the question is there some way of rewriting this general problem, and specifically rewriting it to take this recursive nature into account? And what we mean by this recursiveness, we'll see that in a second. But in general, it again boils down to the simple idea that in more or less any dynamic choice, or more or less any dynamic choice, always boils down to a trade-off between just today and just tomorrow, or just the rest of the planning horizon. Okay, and this tends to make things potentially much more simpler. Okay, because we split this problem basically up in two smaller parts, which seem to be which could be easier, which could be solved more easily, and which also could be implemented in a numerical framework more easily. And this is what people call dynamic programming. Okay, so dynamic programming is a specific way at looking at those intertemporal problems and solving those. Okay, so we've seen the Lagrange approach is, so to say, the direct attack. The dynamic programming is the more sophisticated approach. At the end of the day, both yield the same, both are the same in nature, in a sense, but the dynamic programming approach is much more suited, for example, for numerical solutions. Okay, and the idea is very simple, and I just due to the time restriction, I do not want to dive too deep into this dynamic programming now, but postpone it to next week. But just for you to have a sneak peek on what is going on. So the general idea is the following. suppose you knew the optimal path. Okay, so suppose you knew what to do optimally in every at every point in time, and you also knew the optimal state that you would follow. Okay, given some beginning state. So you knew the optimal the optimal sequence of controls and the optimal sequence of states. So basically, you assume that the problem is solved. Okay. Then you could think, okay, if I move along this optimal path and I just pause at some specific point in time, say at tau, and now I'm giving the chance to re-optimize everything. How would I then behave? Would I then re-optimize, or what would be the optimal thing to do from there on? Well, the thing is, if I pause at some point in time tau, and I'm confronted with a specific state in tau that is the result of me following the optimal path up to tau, what would then be the best thing to do? Well, the best thing to do would be to stick to my deterministic, because it's a deterministic problem, to my deterministic plan, and just follow the optimal path again on starting from this tau. So what we know is, or what we assume at this stage, and we show that later on, that this optimal plan is time consistent, and this time consistency is helpful because then we know that everything we do and everything the optimal plan that we follow and everything what will be in the future is just a function of the current state. So this is just a function of what we are in today. But then we also know that the situation that you are in tomorrow only is affected by the state that you're in tomorrow. And then you see, okay, now maybe it already becomes a little bit clearer. Now there's the trade-off, right? Because my control has contemporaneous effects, but also changes my situation starting from tomorrow. But if I have an object that incorporates all those effects that start from the new situation as of tomorrow, well, then I could think more thoroughly on how to find the optimal solution. And this is basically what we are going to do on Tuesday. So I will present you again a very simple construct of writing a general dynamic optimization problem in this dynamic programming dynamic programming style, and we will then, starting from there, again determine the first order conditions, compare this to the Lagrange approach, and show why this is more suitable for basically numerical for numerical applications. But again, this is what we are going to discuss next week. So for today, I think we just call it a day if there are no more questions. And thanks again for attending, and thanks again for having me. And hopefully this was a little bit insightful. And yeah, see you all on hopefully on Tuesday.